Hello, I'm Gabrielle Hempel, and welcome to Quantum Computing and Cryptography, an Introduction. You should take this course if you work in a field that involves cryptography and advancing technology, if you work with agencies that cater to national security and the ever-changing security landscape, or if you have an interest in cryptography, quantum physics, and quantum computing. A little bit about me. I'm a science nerd with a variety of interests. I studied neuroscience and psychology for my undergraduate degrees, and I'm currently pursuing a graduate certificate in advanced computer security from Stanford, with emphasis in cryptography and secure design. I work as a security analyst by day and a genetic scientist by night. You should already have a basic understanding of computer science, bit level specifically, so understanding how binary digits and how they work in a computer system, have a basic understanding of physics, one and two dimensional motion, forces, and Newton's law of motion, relativity, and then understand the concept of cryptography, i.e., what a cipher is and common methods of encryption, symmetric key, public key, etc. By the end of this course, you should understand and be able to explain the difference between a traditional bit and a qubit, explain the basic structure of a quantum algorithm and how it differs from a classical algorithm, and name obstacles in the development of quantum computing and cryptography. So what is quantum computing? Quantum computing is simply computing utilizing theories common found in quantum physics. These tend to be superposition and entanglement. Superposition is the principle of existing in multiple states at once. Essentially, each element exists in all possible states at the same time. For example, off is also on, up is also down, left is also right. You get the picture. There's also entanglement, which is when two or more objects are permanently linked and one cannot be described without full mention of others, even if they're far apart. Einstein referred to this as a spooky action at a distance. Systems instantaneously influence each other. Now that we have that out of the way, we can get into bits and qubits. In classical computing, we use bits, which are small units of data that are comprised of a single binary value, 0 or 1. A quantum computer, on the other hand, maintains a sequence of qubits, which can represent a 1, a 0, or any quantum superposition of those two qubit states. They're ideologically the same, however, they are 0 and 1, not 0 or 1. Using these bits, we can work on quantum algorithms. Quantum algorithms are initially structured similarly to classic algorithms. A problem is encoded by setting initial values of the qubits, similarly to how we set initial values for bits for classical computing. The calculation ends with the measurement or an unobserved quantum state. When the calculation ends with the measurement, the system of qubits collapses into 1 of the power of 2, 2 to the nth eigenstates, where each qubit is 0 or 1, essentially decomposing into a classical state. If there is no measurement, then the result is an unobserved quantum state. Essentially, these begin and end like classical algorithms. Quantum algorithms provide solutions with certain known probabilities. One of the most well-known, shown on the right, is Shor's algorithm. Simply put, this solves this problem. Given an integer n, find its prime factors. So why do you care about Shor's algorithm? This is one of the algorithms popularly indicated in quantum-resistant cryptography. It processes data faster than classical algorithms, and if an efficient quantum machine was built, it could theoretically break public key cryptography schemes. This brings us to quantum-resistant cryptography. Ideologically, it's secure against an attack by a quantum computer. Current classical algorithms rely on one of 3 math equation types. These are integer factorization, discrete logarithm, and elliptic curve discrete logarithm problems. A quantum computer could easily solve these. Cryptographers are trying to stay ahead of technology and develop algorithms that will be resistant to being solved once quantum computers are a viable threat. Interestingly, most current symmetric algorithms and hash functions are relatively secure against quantum attacks. Increasing the key size can stave off attacks and make them harder to break. Some current quantum cryptography methods. We have lattice-based methods, which involve lattices in their construction, creating a matrix that is resistant to attack. Multivariate, which is asymmetric and uses multivariate polynomials. You should remember those from high school math class. Hash-based, based on hash functions, combine a one-time key with a Merkle tree structure. A Merkle tree structure is when every leaf node is labeled with the hash of a data block, and every non-leaf node is labeled with the cryptographic hash of the labels of its child nodes. We also have code-based, which relies on error-correcting codes. Those control and correct errors in noisy environments. We have supersingular elliptic curve isogeny, which sounds a lot scarier than it is. It relies on supersingular elliptic curves and supersingular isogeny graphs to replace classic Diffie-Hellman ciphers. These essentially establish a secret key between two parties over an insecure channel. They also support perfect forward secrecy. Finally, we have the symmetric key, which you should also be familiar with. These are classic ciphers that are resistant to quantum attacks, provided that the key is long enough. With the development of these, we also run into some obstacles. There is the need to control or remove quantum decoherence, which is a result of external interaction. It's essentially when a quantum system is not isolated, coherence is shared with its environment and it appears to be lost with time. Therefore, quantum behavior is lost. It's also hard to maintain the state of qubits long enough to complete some algorithms. These take a long time. Qubits are easily corrupted. Finally, error rates are large and sometimes cannot be solved using quantum error correction. Many different models and candidates for functional quantum computers are being explored. There are quite a few large companies that are currently trying to generate commercial quantum computers. One example is IBM's Q quantum computer, shown here. As a wrap-up, in this course, you should have learned how to explain the difference between a traditional bit and a qubit, explain the basic structure of a quantum algorithm and how it differs from a classical algorithm, and name obstacles in the development of quantum computing and cryptography. I hope you enjoyed learning about obstacles and development of quantum computing and cryptography, and I hope to join us next time. Thanks.